That's the first thing I'm going to say is when you see hypothesis test and significance test, they mean the same thing. So we're going to talk about exactly what these things are. Much like we did with confidence intervals, we're going to talk about what these tests are, and then we're going to see how we can sort of calculate them or conduct the test, really is what you say, sort of longhand, and then we're going to see how we can shorten it by using our graphing calculator to help us. So very much the same method that we did in the first 3 lessons of this week. So here's the example that we're going to look at through this one. And this has to do in 2020 with the NBA. So the season was cut short by COVID. So they decided to test quarantine all coaches, staff, and players, flew them out to Disney World, and they played in a bubble in which they could not leave or could not go into to finish the remainder of the season. So all teams played on a neutral court, no fans in the stands, yet the league randomly assigned each team to be the home team in 4 of its 8 remaining games to play. Each team had 8 games left to play. To give some semblance of a home court, they lit up the walls with home team logos, projected fans' faces on the screens, played familiar home arena sounds, even displayed virtual cheerleaders. Okay? And out of all of that, of the 88 games that were played, the home team won 49 times, which means the away teams won only 39 times. So the question is, do home teams or did home teams have an advantage in this bubble? Okay. So just like we've been doing before, we can kind of look initial inspection and then have to look a little bit deeper with statistics. So the observation right now is of the 88 games played, the home team won 49 times, or 56%. Okay? And we're asked to say, was there a home team advantage? Okay? Which means the home team won more than 50% of the games. Okay? So the first hypothesis we're going to have is we're going to say status quo. Okay? There was no home team advantage. We just got that 56% by chance. Okay. Hypothesis B is there was a home team advantage, and they won more often because there truly was some sort of advantage. So which hypothesis would you assume to be true? Well, it's a tough one. Because sort of knowing, you guys are probably figuring it out by now that, well, yeah, it's 56%, which technically is home team advantage, but it doesn't seem by a lot. So maybe that did happen by chance. If you're thinking like that, good. Okay, because now you're thinking critically. So really, it's kind of hard to say. Like 56% is more than half, which we would assume would become a home team advantage. But maybe it happened by chance. And we sort of already answered the next question. If there was no home team advantage, that's hypothesis A, what proportion of games would we expect? Well, we would expect 50%. Because, I mean, basically, if there's no home team advantage, it's kind of a coin flip as to how many games they win and lose when they're the home team, and it just evens out in the end to 50-50. Okay. If hypothesis B was true, we would expect it to be greater than 50. They'd be winning more than 50%. Okay. So I'm just going to leave it as 50%. So to sort of restate the question, and often we use this phrase "in a world where." So in a world where there is no home court advantage, is no home court advantage. Hypothesis A, not the status quo. What are the chances the home team wins the result that actually happens? Wins 56% of the games, or 55.7. If that probability is high, then we say, okay, it's likely to happen by chance alone. If that probability is really low, then we say, well, no, that's not likely to happen by chance alone, which suggests that there is a home team advantage. Because the probability is so low, that makes it unusual. Okay. So what was done, as often is done, there was a simulation performed of 100 seasons, assuming that the home team won 50% of the time. Okay. So P is the true proportion is 50%, or the assumed proportion, I should say. Then we get our sample proportion of 56%. The question is, what's the probability of this happening compared to the rest of the seasons in the simulation? You can see, once again, that when we do this, it takes a normal shape, which is going to allow us to do normal calculations, which we'll see a little bit later on. But right now, we can use the dot plot. So estimate the probability. So remember, there's 100 dots in here. How many times did we get 56% or higher? Count the dots. 1, 2, 3, 4 at 56. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 out of 100 seasons. Or 14%. That's the probability that a team would win 56% or more. Which is not really that low. I mean, it seems low, but we're talking about, like, for it to be unusual, the probability has to be really low. We'll talk about a guideline in a second. So does your answer from above convince you that you can reject the first hypothesis that there was no home court advantage and basically say we have convincing evidence there was? No. Okay? Because we can say no because the probability of winning 56% or more games It's not that low. Which means it's not unusual. And how low would your answer have to be in order to convince you? Well, we talked about this before, not 10%. What was the confidence interval we were normally calculating at? 5, right? Okay, so it's actually 5% is a good guideline. It doesn't have to be, it can be 10%. It can be 1%, but 5% is sort of generally the accepted guideline. 5% or lower, because it would be considered unusual. Would be considered low or unusual. Okay. So how do we know when we're performing a kind of test like this? Is we want to find convincing statistical evidence. What we did on the first page was not convincing statistical evidence. What we did on the second page was much more convincing. So when you see the phrase, convincing statistical evidence, that means that you are going to be performing a hypothesis or what's called significance test, either one. Okay. Okay. So how do we start these tests? We always start, and this is actually in, like, we're going to do the state plan, do, conclude thing again. This is actually in the state section. You're going to state 2 hypotheses. Okay. One is like the status quo, which we call the null hypothesis or H0. Okay. This is the default belief or status quo. Nothing's shaken up. Often it's called the dull hypothesis because nothing's happening. Nothing new's happening. Nothing's changing. Okay. We assume that it's true until we are convinced otherwise, and that's going to be probability. It's going to convince us otherwise. The other hypothesis, the change one, that something's changing, is called the alternative hypothesis, HA. And it's our unproven belief, because we haven't proven it yet, about some parameter value, proportion, mean. You know, somebody claims that 40% of people watch a certain show on Net, or 40% of people in Canada watch a certain show on Netflix, or have at least watched one season or something. Okay. 40% is the null hypothesis. Greater than 40% could be the alternative, because somebody else comes along and says, no, it's actually bigger. Okay. So It's often called the research hypothesis because it's what we're researching into by calculating probability. Okay. And it's not assumed to be true. We have to collect evidence. Innocent until proven guilty. Null hypothesis until proven alternative. Okay, so going back to the example we've been working on, this is how we would set these up. Sort of a written version I'll write, and then this is the one that we normally write, the numeric where we involve numbers. So remember we said no home court advantage. And what we were trying to collect evidence on was home court advantage. But we normally don't write it out using words like that. We're going to use notation. Okay? So remember we said no home court advantage would suggest that a team's winning 50% of its games. So that means the proportion, not the sample proportion, okay, the true proportion is 50%. We are trying to prove the alternative, just one second, that there is a home court advantage, which means the proportion of wins must be greater than 50%. Oops, it's greater. And then we always add this to it, what P is, the true proportion of games won by the home teams. Ellie?
Is it always going to be out of the proportion as 50%? Is that for this?
Oh, that's just for this one. Yeah. Often it could be 50 because often you're, you say you're making claims about, somebody says the majority of people support this. Well, the null hypothesis would be 50%. The majority would be greater than 50%.
It's not to figure out what.
You would be given it. Yeah. Okay. So, in a world where the true proportion that wins the games is 50%, what is the probability, or what are the chances of our sample proportion is 56%, which means the true proportion would be greater than 0.5. Okay. This is very important, this next one, okay? You never accept the null hypothesis. The null hypothesis is an assumption. You're assuming something to be true. That doesn't mean it actually is. So you can actually never accept it. You either, and I know this sounds weird, the phrasing, you either reject it if it's not true, or you fail to reject it if you can't find convincing evidence. Okay. Because HO is always assumed to be true. That doesn't mean it actually is. So like I said, we can't accept, we either reject the null hypothesis, HO, or we fail to reject it. If we reject it, our probability value, which we'll call a p-value, the probability is less than the percent we decided on, normally 5%, which we call alpha, okay? Or significance level. So if our probability is less than 5%, if we use 5%, we reject HO and we have convincing evidence of the alternative hypothesis. But if that p-value is greater, which we found out in the NBA bubble one that it was, we fail to reject HO, or we don't reject HO, we don't have convincing evidence. And this is what the conclude sentence basically looks like. Because our p-value, okay, whatever it is less than our alpha value, or significance level, or alpha level, pardon. So this p-value will be the probability that we're going to calculate. Alpha level is what we decide what's going to be, what our guideline is going to be to determine whether we reject or fail to reject. So like I said, if it's less than, then we reject HO. And we do have convincing evidence of HA. If it's greater than the alpha level, we fail to reject HO. We don't have convincing evidence. Okay. I just wrote the bottom, didn't I? Why didn't somebody tell me? Okay, well, now I've basically showed you all of this. So, the p-value is the probability, like I said, of observing your measured stat value. Okay? If you assume the null hypothesis is true. And it helps us determine how unlikely our sample data is, or unusual. And then we calculated this, it was 14 out of 100, which was 14%. Okay, so interpret it, well, in a world where there's no home court advantage, there is a 14% chance the home team will win. %56% or more of the time. That's what that means. And I've already said this, the alpha level or significance level, denoted by the notation, the alpha symbol, that's the cutoff. Okay, that's the guide. If our probability is above, fail to reject. If our probability is below, reject. So the significance level, like I said, the most common one is 5%. Okay? So we would say 5% for, because we usually answer in decimal, we do question 0.05. Okay? So we would reject the null if our p-value is less than 0.05, but then we would fail to reject or don't reject HO if the probability we got, the probability value or p-value, was greater. So if we connect these two, we make our conclusion. The p-value 14% is greater than the alpha value. Yeah, it's, I mean, can't draw it exactly, but it's kind of looks something like that, like almost like a fish. But that stands for alpha. That stands for. So, again, in a world where the home team has no advantage, chances and when I say that, I mean p-value that home team won 56% or more. So that's going to be a very simple question. Okay. And then compare it to the alpha to get your conclusion. So we would say because our p-value 14% or 0.14 is greater than our alpha level. (0.05). We fail to reject HO. We can't reject it. We don't have convincing evidence. There was a home court advantage. We can be even more precise than 14%, okay, which we'll talk about later on. Just one final thing, I'm not going to write anything anymore. But just quickly, there is a connection between these hypothesis tests and confidence intervals, because if we took the same NBA bubble example and calculated a confidence interval, we would get 0.453 to 0.661. In other words, the number of wins, or sorry, the percentage of wins could be anywhere from 0.453 or 45.3%, which means definitely the home court team doesn't have an advantage, the away does, all the way up to 66.1, where the home team has a significant advantage. Well, 50% is in this interval. So it's possible for 50% to happen, which means there's no advantage, which is the same conclusion we arrived at when we did that hypothesis test. Okay.